Okay, this video is going to cover relative momentum and energy. So let's get started. Let's review classical momentum. The equation is that momentum equals mass times velocity. So let's go through an example. Let's say we have a car that has a mass of 2,000 kilograms and has a velocity of 20 meters per second moving to the right. In addition, let's say that there's a truck that has a mass of 3,000 kilograms and has a velocity of 15 meters per second moving to the left. Let's say that these two vehicles are on a collision course, and once they crash, they lock together and become a new unified mass. So if we wanted to calculate the momentum after the crash, we could look at the data from before the crash and take the car's mass and velocity and multiply those together and find its momentum before the crash is 40,000 kilograms meters per second. And we can take the truck's mass and velocity before the crash and multiply those together and calculate that the truck's momentum before the crash was 45,000 kilograms meters per second. And since the truck has a larger momentum before the crash, we know that after the crash, the vehicles are going to move to the left. And so we can take the smaller momentum and subtract that from the larger momentum and calculate the momentum after the crash to be 5,000 kilograms meters per second. Now that we've gone over an example and reviewed classical momentum, let's dive into relativistic momentum. So the equation is a little different, but still fairly similar. M is the rest mass of the object. U is its velocity relative to an observer, and gamma is the relativistic factor. To calculate gamma, we use this equation here, and all you need to know is the velocity. And you can calculate the relativistic factor. So at low velocities, at non-relativistic velocities, the relativistic factor approaches 1, so it doesn't really play a role in the equation, and you would just use the classical momentum equation. For example, if the velocity was 25 meters per second, then the relativistic factor would be 1.000001, which is pretty close to 1 and wouldn't have much of an effect on the momentum. But at speeds that are a tenth of the speed of light or greater, it's recommended to use this relativistic momentum equation. And if we were to calculate the relativistic factor at 1/10 the speed of light, we would find that it would be 1.005, which would change the momentum by 0.5%. So like classical momentum, total momentum is conserved whenever the net external force is 0. And it still follows the general trend that objects with a greater mass and velocity have greater momentum. Let's do a practice problem. Let's say you have a spaceship and you have your relativistic momentum equations, and you wanted to find the mass of that spaceship. And you know that the momentum is 5.5 times 10 to the 12th kilograms meters per second. And you also know that the velocity is half the speed of light. And this velocity has to be relative to one observer. So we'll put an observer there. And there's two ways to calculate the relativistic factor. Once you have this information, you can either put in for the velocity 0.5 and for the speed of light 1, or you can put in for the velocity 1.5 times 10 to the 8th, and for the speed of light 3 times 10 to the 8th, and calculate it that way. Either way, it both works. So if you were to calculate this and to solve for the mass, you'd find that the spaceship has a mass of 25,927 kilograms. Another interesting thing about the relativistic factor is that because of the equation, you can see that as the velocity of an object approaches the speed of light, the relativistic momentum approaches infinity. Now we're going to go over energy. Let's start with classical energy. One important law about energy is the conservation of energy, is that energy can change form but is never lost. For example, you can have mechanical energy, which turns into electrical energy, which turns into heat energy. And so you could use mechanical energy to crank on a generator to make electrical energy, which then could be used to power a toaster to heat your toast. So with relativistic energy, it's very, very similar, except for this to work, you have to include that mass can be transformed into energy. An example of this is the sun that is doing this all the time. So there's the equation for relativistic energy. Again, we're going to use the relativistic factor and multiply it by mass and the speed of light squared to find energy. So let's try a practice problem. Let's say that an object has a mass of 50 kilograms and is moving at a velocity that is a quarter of the speed of light. So from this information, we can again plug in a 1/4 for the velocity, and we can plug in 1 for the speed of light to calculate the relativistic factor, and multiply that by the mass, and then square the speed of light, and find that our energy is 4.65 times 10 to the 18th joules. So thank you for watching this video. I hope it was helpful. Here's some of the references that I used.